Okay. Thank you. Okay, great. Great to see so many people here today. Welcome to GeoOnsdag, our monthly series of lectures for in geosciences on different topics. This is something we started a few years ago and really love doing. So the idea is to give an idea about some of the research that's going on in the department. This one, I was thinking yesterday was my niece's birthday. Not that anybody really cares, but my niece is she's in the United States, and she was a physics major like I was, and she went to the same college that I did. And anyway, I'm old-fashioned, so what did I get her for her birthday? I got her a gift certificate for books, old-fashioned books, you know. And she wrote back, she said, "Oh, great, well, I want to get this book, Project Hail Mary," because she had just seen this movie, Project Hail Mary, which is about flying, unwillingly it turned out, to another planet to do an investigation. There were some aspects of the physics were realistic, some maybe not so realistic. The bacteria eating the sun, I think, was probably not exactly believable. But anyway, the point is there's a lot of interest now about exoplanets. You hear it too about information coming in all the time from the James Webb Observatory and so forth, and we're all following this very closely. So this is a super interesting topic. Today's speaker is Stephanie Werner. So she's a professor here. She comes from Germany. So her PhD was from Berlin, is that right? At the Free University, so you didn't have to pay anything. That's perfect. And came to us during the previous SFF, right? During the seed, so no, did not. Okay. Earlier, it came even earlier, okay. But anyway, she is currently the leader of FAB, which is it's a wonderful sounding center. It's the Planetary, despite this word being English, I can never get it right, habitability, there we go. Planetary Habitability, FAB, and that's it, Planetary Habitability. Thanks, okay. And anyway, but so she can tell you more about that. So please welcome Stephanie.
Okay, thank you very much for all coming. So obviously the calendar invite did some good to many of you. And also I got the permission of Joe to speak in English, although I should try more often Norwegian, but you will get it in English now. So today I talk about exoplanets, and I want to introduce you to about where we find them, what type of planets they are, and do we know enough? And that why near and far, small and rare, large and plenty. So for all of those who have only heard about planets, there is an Astronomical Union definition of what is an exoplanet, and the big difference is that planets are only planets when they circle around the sun, and they're called exoplanets for all other stars. So it's quite simple, and it's nevertheless a very confusing definition, because in general they are all planets and of various kind. When we want to search for them, we can find exoplanets obviously everywhere, but to prove that they are there, we need to be able to see them, and seeing is something which is not exactly straightforward. So one of the ideas is that we can calculate probabilities looking at this beautiful picture of the Rubin Observatory with the Milky Way in the background. A lot of stars there, and many of these stars, if not actually all of them, may have or do have planets. Correction, exoplanets. So but do we see them? And there's a few objects which we have observed directly, not we, but the general we. So you have an example, and that is because the planets are much more fainter than the stars itself. So this little yellow star in the middle is where you cover the actual star up, and then you can see the faint light of the exoplanets circling around. And this was one of the examples where you can see 4 objects moving within several years, as you can see the countdown there, and that is a wonderful name, HR 8799 system, discovered in 2008. And for the idea what it is a 30 million years old system, 133 light years away from the Earth, and of course the Sun. And it is a star, which is, you don't see at the moment, 1.5 times the mass of the Sun, or 5 times almost the brightness. And if you don't understand the scale of this thing, so you have the scale bar, 20 astronomical units in the bottom, and 1 astronomical unit is the distance, average distance between Sun and Earth, so very Earth-centered definition of distance. If you want to have it a bit more precise, it's also given in meters, light years, and parsec, all astronomical measures. So the peculiarity of this kind of ability of seeing objects directly is you see from the top on the system, so you see them moving around. The more typical way of discovering exoplanets is actually by them passing in front of the star. Here's an example from the solar system from June 2012, where you see the little dot in front of it, and that is Venus passing by, observed in the wavelengths, which is highlighting hydrogen alpha. And if you wonder whether that is a common feature or not, or is it easy to discover exoplanets by transit, you need to think that between you and the star, this object needs to pass, and that means you have a very narrow angle of viewing. And also for the observation of Venus transit, if you didn't see it in 2012, I think the least of us in this room will see it next time, which is 2117. So it's a rare event. So the principle of transit is depicted here. So you have the planet moving in front of the star in our line of sight, and as long as this planet is in front of the star, the brightness which we receive, so we have the star only resolved as one point or small point, little extended point, which we see the brightness variations. It's a little more complicated, but in principle, if the planet is in front of it, it covers part of the disk of the star, and therefore we will have a little dim down, and that is shown as the below light curve. So with this, because we see the dimming down, we can, in the transit period, we can determine the radius if we know the star size. So it's the ratio between cover up and full star. The other method on how we can see planets is by the wobble of the star. The planet is introducing as it is pulling on the star, making it move around the common center of mass. So when we observe with the spectrometer these objects, we see that the spectral lines slowly move back and forth. All of you have probably heard Doppler shift, and this moving around to the blue and to the red is drawn in this sinusoidal curve as the phase shift, and depending on how strong the planet is, so how massive the planet is with respect to the star, this is stronger and less strong deviation of this Doppler shift. So with this, we can determine the mass. And you already recognize we can either determine radius or mass, or we are lucky that this object is actually wobbling the star and also transiting. So it's an even more rare event to know both parameters. And since that is a little bit theoretical, here's an example of how on the left side is an example of how this light curve looks like. So you need the thin gray lines measurements. You produce a model of thinking how this radius size is, and you get then the black line with the red dots that's how you see a planet in transit. And the wavy part, again, you have a number of observations of this wobble of the planet, and you can then, with a model, interpret the light curve or the phase shifts to interpret to be a planet there. So you see, it's not exactly seeing an object. And that it is actually a methodological bias in these two things. We see on these two diagrams. On the left side, mass against how far away the star is, and on the right, the radius against how far away the star is. And by the clustering, clearly the different colors show different methods. The weird color is the transit, and then there's some other radial velocity, so you see it's not the most common way of discovering planets any longer, and then some other methods, micro lensing and direct imaging, as you have seen before, all possible ways of discovering exoplanets, but as you can see, it does not cover the full mass range and the full radius range, or even the full distance from us towards away from us. And that is to give you a better impression, because distance to the host star in parsec doesn't mean much for you, but maybe in a picture with respect to the galaxy, you can look at it like this. So this bullet goal thing is centered on the sun with respect to the Milky Way galaxy. We will never see it like this because we're not flying above the galaxy from the top. But you see here in, again, parsec, and you can calculate how much astronomical units this is, all numbers which we cannot really imagine. The most furthest away discoveries are by microlensing, and that is a constellation which is very unique between us, some heavy object, and it is then bending the light from the star behind you, and you can see then a potential object. And the red part is the transit method. So you can see that we do not resolve stars far away. Microlensing the only way. Transiting quite distributed and so on. And then there's some other methods which I don't go into depth. So you have clearly a biased way, and we only find exoplanets in the Milky Way because that's how far we can see. And if you wonder what's the closest, that's somewhere very much in the middle here, is the star Proxima Centauri. It's what is called flaring, so it's a very active M-dwarf. It has a surface temperature from about 3050 Kelvin, so only half as hot as our sun. It's about 4 light years away, and it has a planet. And this planet is 1.3 times the mass of the Earth. It is very, very close to the star, so it is taking only 11 days to circle around the star, compared to our 65 days, totally different dimensions again. And because the star is much smaller than our sun, what we call habitable zone, and I will come back to that, is much closer nearby, so that actually this planet is in the habitable zone of that star. And if, because of the closeness, it would be the go-for planet and all these fantasies you introduced, number one. But whether or not we can live there or reach is a total different question. So a little bit historically, we have exoplanet sciences since, now I have to calculate, 31 years. So it's a very young science. The main discovery was Pegasus B in '95, based on radial velocity measurements, and that kicked off a lot. Obviously, this is so exciting that you get a Nobel Prize for it. But after that, there were several missions, and on the top row dedicated to exoplanet research, and on the bottom row, the typical telescopes which you can use to do measurements. So we are at the moment in the awaiting the Plato launch, and I will come back to that. So, but what have we found so far? So there is exoplanets, and there are wonderful worlds, or you wonder about the worlds. Some of them I will introduce closer, but you see there's some where the planet's atmosphere is sucked up by the star. We have the color of the planet, maybe purple. We have also, as proposed in science fiction already, worlds with two suns. We have, I will come back to some of the others, we have physical conditions which makes it to interpret that we have glass rain in these atmospheres. So whatever you want to think about. But now I will introduce you AUMIC B. That is, it's an infant system, and it was actually known because of again, I need to explain maybe a little bit. So you have the star in the middle covered up, and you can see from edge on the protoplanetary disk, so the dust which is circling around the star. And what has happened is that they observed several years after each other for defining things, where they figured out that there is quite some movement in this dust disk. Also, when you determine the age, actually it's a very young red dwarf again, 31 light years away. And when they look then closer, not only that they have movement in the disk, but also in the light curve, they found features of at least 2 confirmed planets. And if you don't really know where you see this in the light curve, so you have a variation in this star itself, and marked here, this little blip and a little blip here, that's the planet. So again, you need to trust measurement skills of the astronomers. So the other, and that is maybe a little more peculiar, it was promoted in 2013 as the first cloud map of an exoplanet, and in this specific case, Kepler 7b. It is circling a hot Jupiter, and that means a Jupiter-like planet. In this case, half the mass of Jupiter, 1.5 times the Jupiter size, 1,000 light years away. Because it is so close to the star, 4.5 days of rotation period, it is extremely hot on the surface, and the density of the planet is only 166 kilogram per cubic meter. So the postulate in 2013 was that because when you interpret the light curves, so pink is the total, and then if you assume either thermal emission because it's heated up on one side more than the other, or because there is something higher up than on the other side which reflects, you can interpret either a cloud deck or some kind of thermal event. In the earlier phases, it was suggested that it has an inhomogeneous silicate-based cloud cover, which was a little bit corrected a little later on, because it sounds really like a weird interpretation. But if you don't understand how to imagine these kind of curves, there is always the artist impression which helps. So the next peculiar object is actually, you maybe remember from the media, K2-18b, which has been in the 2019s observed by Hubble, and that is the light curve. Again, you can see in black the measurements, and then in colors the proposed interpretation of for a specific composition. In this case, either water with clouds, water with nitrogen, or water only, and you can make your own judgment whether or not you believe this interpretation. So, but then quite a bit later, 5 years, when James Webb Telescope was active, we got this spectrometer, and the difference is, so we have wavelengths from 1 to 1.7, and in this case from 1 to 5, meaning that the overlapping range is just this part here. So the measurements look worse in white dots. The eye sees only the blue line, which is a postulated spectrum which includes methane, carbon dioxide, and you can judge again yourself how you interpret the validity of this postulate. What came out of it is that because of the composition, interpretation went from super Earth, because this object is 2 times the size of the Earth, to mini Neptune, and that is not only the difference in spectrum interpretation, but also in the idea of how we think about the structure of the planet. Obviously, I pointed out this one so that Vincent get a heart attack, because there's dimethyl sulfide interpreted into a way which one can debate very much. Maybe you know that this is some rotten bacteria, and I don't want this in the press. So, because whatever you want to discuss about this one, the outcome was obviously headlines like this, and that is maybe good for funding, but definitely not good for science. So another object is 55 Cancri system. It's a binary star system about 41 light years away. Star A is depicted here in this diagram, which has 4 confirmed, maybe 6 planets, and shown only 4. And the dimensions with respect to the solar system you can recognize. The second star is called B. Has probably 2 planets. It's much smaller than the Sun. But planet A, star A, is interesting because it's older and smaller than the Sun, and that makes it having a different composition, which is called supermetal rich, and that means you have proportionally higher carbon and iron content in the star. So out of this, and the constellation of the object towards the star, so the planet E, which is the closest in, is a super Earth with an orbit of only 18 hours, and that means it has a surface temperature, and now it's at Celsius of 2000, and that means it's so hot there that you can melt even rock. So the idea is that we have not a water ocean like us, but a lava ocean on the surface of the planet, at least on one side. Because these objects are bound in their rotation as a, how you call it in English? Tidally locked. So, okay. However, because of the carbon and iron content, there is, of course, possible to calculate what kind of chemical conditions there are. So you can postulate that it is carbon-rich much more than us. So you can either make it a diamond planet, glittering diamond rain, or whatever diamond, because it hits the headline. So you can see the object twice the size of the Earth and glittering across the cosmos. Such headlines made some smart people wonder about how life, the world, and science is going. So there was a commentary about strange news from outer stars, where they pointed out these people who discover planets, exoplanets, should learn a little bit from geoscientists. So that was my introduction. Now we get into what we actually know. So we have seen in the beginning that we can find the objects by mass, or where we know the mass and radius, and that is shown here. So again, bullet chart with the distance from the star and mass or radius. And to make it easier for you and not to need to read all these small numbers, the Earth is pointed out there. So all these objects are more massive or larger and generally closer to the star when you determine by radius, and a little more complex when you have the mass known. And of course, the more planets there are, the more planets and around other stars, it raises the possibility of life elsewhere, and obviously for all the young, bright heads, a new opportunity. So, but what can we do? So we have one parameter. On the other parameter, we can, of course, then think about mass-radius relation in the galaxy. So you can see before we had about 4,000 objects in each panel, but for only 2,000, at least a year ago, the mass and radius was known. So you can make a mass-radius relationship plot, as shown here. Again, Venus and Earth down there, Uranus, Neptune, Saturn, and Jupiter. And if you think about it, it is actually possible to put some power laws through these lines, and that has been done, showing here. And you can classify them in then Terranian worlds, which have almost no atmosphere, Neptunian worlds, which have growing volatile envelope. If they get very big, they start to do very strong self-compression against the heat of the interior, and that is then passing into the Jovian worlds, where if you get the mass much larger and larger, you enter the star environment, because then you ignite the interior to do hydrogen fusion. So obviously, this idea is an astronomer view, because you have some patterns to recognize. We can also then compare to the stellar categorization, where we have also something which is a surface temperature related to mass, and luminosity, also a pattern which is useful. And if we then turn it around and put it on there, you have some kind of prolongation, and you could possibly say, from an astronomer point of view, these are just smaller end of the same. But obviously, we disagree. So we can also use the criteria which we have learned from what we use from the transit method. So we can kind of a little bit arbitrarily group them into mini-Earths, Earth-alike, super-Earths, mini-Neptunes, which are all related to the radius classification. And then we come into an area which is just all Jupiters alike. And if we would want to find life, obviously we should limit ourselves to these kind of things. But how close to the R equal 1 do we need to go? Because if we look at these objects, we know that all these small ones, they are not exactly good for life in the solar system already. But if we go to the bigger ones, we know about these Neptune objects probably not exactly having life. But then what about all these objects in between? And they are actually by now the kind of majority of objects to be found. So are they more Neptune-alike or more Earth-alike? And is this one parameter view actually helping us? And you can get my guiding question and answer already no. So we need some other ways. And thinking about the Earth and Neptune, we already know totally different structure for us, obvious as a solar system scientist, definitely not the same. Much other composition, atmosphere is different, interior is different, everything. So obviously the geoscientist or planetary scientist think about composition and structure. So if we plot then the physical growing object for sphere, which is hydrogen and helium, so Sun-like composition or Jupiter-like composition dominated, we get this line, and it fits quite well. If we go then to smaller objects, we still a little too much planetary scientist and think in funny categories. So if we do that for a water planet, which is following then these lines, for an Earth-like planet or an 100% iron planet, we get these lines. But what is clear from this approach is that we do not have a power law or broken power law line how to explain the galactic small body mass and radius relationship. So what we learn is that planets do not grow linearly, because also the small objects have self-compression. And if we want to search for similar type of exoplanets, we need to at least follow these lines of interior structure, similar objects. So, and if we want to then look for Earth-like objects, we need to even narrow down much more, because there's a maximum limit of how these objects survive. So if we want a rocky structure and an Earth-like mean density, and that imposes a maximum limit of radius of 2 times the Earth radius, and masses should be not exceeding 10 Earth masses. And then to be habitable, of course, they need to be in the habitable zone of the planet. The star. So that was from our center proposal. The habitable zone, again, a definition which comes actually from astronomy. It is the presence of liquid surface water for a given distance to a star, stellar luminosity, and planet atmosphere composition. And if we talk about this diagram here, we are in the today, having the Earth spot on the habitable zone. We know we have liquid water on the surface of the Earth. In the past, at least according to this diagram, the sun was dimmer, and that means maybe Venus was more habitable. And in the future, when the sun is getting brighter, and we may leave this kind of habitable zone and Mars enters. Question is there still water? So if we want to talk about habitability in general, at least for astronomical purpose, which the only thing we can judge, it is a star-planet interplay, and it change the conditions through time because the stars change. And do we recognize these kind of things? In a more exoplanet population diagram, it's slightly different plot on the bottom, but it's the flux which is keeping the temperature on the surface of the planet in the right range, but for different stars. So in the bottom, the red dwarf is about between 2,000 and 3,000 Kelvin warm on the surface. We are on the yellow stars. Our planet star has 5,777 Kelvin surface temperature, and further up are brighter ones, and in between you see the surface temperature relationship. All of these objects plotted in radius and with the color, the density, and you can see that almost all of them are too hot. There's a few marked systems, TRAPPIST system and solar system, where you can see that the Earth is just on the edge. We know that as well. But in general, it's a gap or very few objects which are Earth-sized and in the habitable zone of the planetary system. So it's not very many objects we can think of currently to evacuate to. So what we will have now soon, the Plato mission, which is dedicated to find more Earth-sized objects in orbits around the star, which is in the habitable zone, for stars which are similar to the Earth, the Sun. So we hope for that. It will a bit about the Plato mission. So Plato called Planetary Transit and Oscillation of Stars mission. It is to find, as I said, Earth-sized planets in habitable zones around solar-like stars. And the stars will be characterized also by age, and we come back to that. All the details in between are not so important, but the two methods are transit photometry and asteroseismology to do what is highlighted in red. The Plato spacecraft is built up as depicted in the site, and for those who are young and hopeful, actually this kind of, you need to think quite far in the future. So Plato mission was not selected in a proposal 2011, but then selected in 2014. My involvement started also about then. There has been a Norwegian contribution in the hardware of the telescope and also now on the spacecraft, because there's a payload and a bus, usually separated. And currently everything is tested, and the launch shall be early 27 with the Ariane 6 rocket. And data shall come shortly after. So the spacecraft has the dimension as shown here. It has, I forgot now, 24 plus 2 cameras, so that they are installed, that we have in the center of the viewing 24 light curves at the same time, and then further out a bit less. The real spacecraft looks like shown here. And what is more exciting maybe, these cameras have names. And the Norwegian camera is called after Christopher Hanstein, Norwegian astronomer and geophysicist. So let's hope that this is not the camera which fails first. Okay. So the viewing strategy is as most of the telescopes. I'm not so sure. So we have the sun, the Earth, the moon. And if we take the gravity fields of all of this, we have points where we have gravity of these different objects canceling each other out. One of them is the Lagrange point, as shown on the most right side, and that is a stable point for telescopes. So where we place many telescopes, including also Plato. So that makes it so that it doesn't need to move a lot, but to view always in the same point, and it is moving around, it has to, of course, rotate 4 times over the orbit it makes. And that is to confirm the viewing of field, the first field, which they will look at 2 years, and then maybe move, or 4 years, depending how many exciting objects they have found. Okay, and now I'm totally out of time. Okay, I will try to see how much I can rush through the next 20 slides. So, our view on from the Earth to the sky. If we want to find star-planet formation places, we need to look in the sky a bit like this. And we can look at Orion, for example, where we have the Orion Nebula, and if we zoom into this Orion Nebula, we have again these star-forming sites, which are depicted, several examples here, in different wavelengths. And if we take these kind of objects, they look like this. And you can see that that star-forming regions, which have peculiar disks around them, and these disks may or not be promising protoplanetary disks for planet formation. So why is that so important? Because we want to think about how many objects, how likely it is that the planets form, and whether or not we can characterize these exoplanets better than just by mass and radius. So that is then how we think planets form. We have the star in the middle and the protoplanetary disk around. There's a temperature gradient, and according to this temperature gradient, this dust has different composition according to condensation temperature of the material. So closer in, we have rocky and metal material, and further out, we have ices. So out of this, we have formed the rocky planets in the solar system much closer to the star, and the more volatile rich objects further out. So how do we marry that to what we know about the exoplanet systems. So that looks actually quite different. So again, we have the solar system here with Jupiter here and Mercury and Earth depicted by these straight lines. And you already see, remember logarithmic scale, that all these objects are much, much closer to the central star. So nothing looks like the solar system. And do we understand how to overcome this observational bias? And then, do we know if there's water on these objects? And this blue sketch is the range where there may be the habitable zone if we are generous. So you see there's not much objects currently which we can look for. And if we look at these protoplanetary disks or star-forming regions, so we have in the top row what we see with centimeter wavelengths, so it's the carbon monoxide, the coldest part of the disks, and you hopefully see the square. That's the zoom into the inner parts where we can watch in millimeter scale the dusty part or the particular part of the disks. And if you see the little red circle, the dimensions are 50 AU. So the disks are all kind of 150 astronomical units. And if you know that the solar system is maximum 30 astronomical units, and all these systems here are smaller than 1 astronomical unit, there is somehow a mismatch with the typical observable protoplanetary disks. So obviously, astronomers get challenged. So they find also little dots somewhere with the same method, and they getting into the Neptune orbit dimensions, relative and also smaller. So maybe these are the protoplanetary disks for these kind of systems, but do we form planets which are wet in this kind of or with moisture? A little bit more in the astronomy. So we have our galaxy, which is shown here. And this, if we look at the composition, we are, okay, I can skip many different elemental abundances. We can calculate the composition which should go in the protoplanetary disk, in the planetesimals and blah, 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 blah. So we can do fancy science, calculate them, figure out whether or not we can form with the rock-forming elements planets. And now I have to skip quite a bit, so you can see that I have had prepared how planets look when we model them. Peculiar, but Earth-like, so Earth is down in there. Color code you resemble, but they don't explain this pattern. So we have a very few objects which are Earth-like or whatever, and all of these are totally volatile rich. And how much am I allowed to do? 5 more minutes? Whoa, 1. Okay. It's all about atmospheres, huh? You skip all the atmosphere part, okay? Atmosphere. Oh, you can measure on the Earth changes. You can make a model. Atmospheres. You can measure atmospheres everywhere. You can think about how atmosphere work. So I have to do another talk about atmospheres. Huh? Okay, summary. Plenty more to discover. And if you want to, just think fantasy is the limit. Science fiction is your guide. Incredible range of parameters. And first, physics and chemistry applies. And then we need Earth scientists to help. Thank you very much.
Great, thank you. You can see it's a relatively new science, but there's already a lot to talk about. So yeah, we need to have another seminar to go through this. We have time for
some other candidates here down in the auditorium.
Yeah. We have time for two questions. So who would like to ask a question? Okay, I can take the first one. So the present United States administration wants to go to Mars and set up a moon base. I mean, a manned base. There was Richard Feynman had gave a talk, a lecture about 50 years ago, I think, where he said that would be a rotten idea for various reasons. Yeah, but it got me thinking. I mean, so as Mars drifts into the habitable zone, and it doesn't have water, is there any hope that it could get water by some other means?
Well, there is a little bit ice, so you can melt it.
Yeah.
And then maybe. But I'm pretty sure if it takes 2 billion more years, it may be sublimated, so forget it.
Yeah. Other questions? Okay, no, all right. Okay, in that case, I would like to just make a quick plug, because if you found this interesting, then we are having, we're going to have a workshop next week. So there's a group of people from FAB and also from the section for meteorology and some others who are going to get together and talk about these type of things. So it's called the Early Earth's Atmospheres, Oceans, and Planetary Habitability, or EON. So this is the 23rd and 24th, so this is next week here at the university. Somewhere on, it's at Helge Engshuis, right? So, but a bunch of interesting talks, and with the idea that, that people who are doing Earth's climate and also extraterrestrial climates and so forth can get together and talk about things. So a bunch of interesting talks, so if you're interested in this, so you're welcome to come to that as well. Okay, that is all, unless there's anyone else wants to say anything. Thanks for coming, and we'll see you next month for another exciting GeoOnsdag talk.